Welcome back to B Spice. In this session, we'll talk about gas turbine. So, hope you had watched the previous session on gas turbine basics, wherein we covered the basics with the help of a model. But this is the exact in the sense we'll talk about the air inlet, basically the inlet section and the compressor section and the combustion chamber section and the turbine section and the exhaust section. All these we are going to talk. So yeah, let's start. Okay, gas turbine operation. So this is a typical example, friends. See, a gas turbine has an upstream rotating compressor, right? Coupled to a downstream turbine and a combustion chamber in between. Very simple, isn't it? So there are basic operation of four types actually. Okay, inlet section. So fresh atmospheric air is sucked, okay, and should be free from dust and dirt, as simple as that. Then compressor section. Fresh atmospheric air flows through the compressor that brings to a higher pressure. So this is the point that brings to a higher pressure. Just make a note. Then combustion section. Energy is then added by spraying fuel into the air and igniting it so that combustion occurs. Okay. So one more to add on. Right, turbine and exhaust section. So high temperature, high pressure gas enters the turbine and expands down to exhaust, okay, pressure, producing a shaft output in the process. So the turbine shaft work is used to drive the compressors or pumps and other devices as an electrical generator that may couple to the shaft. Okay, right. One more point, a starting unit, a started unit. I think the typo error, started unit, cranking motor. Okay, is used to, first for the first rotor motion until this turbine rotation is up to the design speed and keep the entire unit running. Okay, so these are the fundas. Okay, component fundas. Now we'll go into the details of each section. Okay, inlet section. Okay. So the air inlet duct must provide clean and unrestricted airflow. Clean and undisturbed inlet airflow extend the life by preventing erosion, corrosion, foreign object, everything, right? So consideration of atmospheric conditions such as dust, salt, industrial pollution, foreign objects like birds, nuts, bolts, temperature must be taken care when designing the inlet system. Okay, that's it, friends. Inlet. Now we go into the compressor section. Okay. So this is a typical example of an axial compressor. I just put for a better explanation. Okay, the compressor provides turbine with all air it needs in an efficient manner, right? So in addition, it must supply air at high static pressure. So that is the point, high static pressure. Okay, so generally axial flow compressors are used. So in an axial flow compressor, each stage incrementally boosts the pressure from previous stage. So single stage of compression includes a set of rotor blade, okay, attached to the rotating disc, followed by the vanes, stator vane attached to the stationary ring, okay. Now, to add few more, the flow area between the compressor blades, as you can see here, the flow area between the compressor blades are slightly divergent, and flow area between compressor vanes also slightly divergent, okay. So you may have a question on this. What is this when we say the divergent? Yes, when we say that compressor blades are divergent, it refers to the shape and arrangement of the blades. Shape and arrangement of the blades in an axial flow compressor. So in this context, meaning in the axial flow compressor context, divergent means that the space between the blades increases. The space between the blades increases as the air moves through the compressor. Okay, as the air moves through the compressor. So this design helps in gradually slowing down the airflow while increasing its what pressure. So that is the point. Okay, so just make a note, friends. Right. So compressor rotor blades convert mechanical energy into gaseous kinetic energy. Right. So this energy conversion increases the total pressure. Okay, we call it as a PT. So most increase in the form of velocity, Pi, and with a small increase in static pressure. So the stator vanes, slows the air by means of a divergent duct shape, converting accelerated velocity to a higher static pressure. So that is the whole concept in this, friends. Compressor section, high pressure. Just remember that. Okay. Now we go into the combustion section. Okay. So this also I try to explain with a simple diagram. Okay. So once the air flows through the compressor, it enters the combustion chamber called a combustor, right? So the combustion section has a difficult task of controlling the burning for large amount of fuel and air. Okay. So the point to take note is it must release the heat in a manner that air is expanded, okay, and accelerated to give a smooth and stable stream of uniformly heated gas at all starting and operating conditions. So that is the point. Okay. So this task must be accomplished with minimum pressure loss and maximum heat release. So that is the point. Okay. Maximum heat release. There it's an increased pressure. Right here it's a maximum heat release, combustion. Okay. Now to add on few more, I just put this analysis the what do you call the analysis picture here. I'll explain one by one. Yeah. In addition, combustion liners must position and control the fire to prevent flame contact with any metal parts. Okay. So 6 combustion liners like can type. There are many type. Can type, I just put it here. Or position with annulus created by inner and outer combustion cases. Just visualize this, friends. You have this where is that? Yes, inner and outer combustion cases. I'm looking for, yes, this is the outer, okay, outer, and this is the inner, okay, this all the inner, and this guy is the outer, okay, just remember that this is the inner and this is the outer combustion, okay, right. So combustion takes place in the forward end and primary zone of the cans. So that is the point here. The primary zone here, the combustion takes place in the primary zone. Okay, just visualize that. So the primary air amounting to one of the 1/4 of total airflow is used to support the combustion process. So you may ask a question, what is the other remaining? Yes, the remaining are referred to as secondary or dilution. Okay. So that also is there, dilution. Where is that? Yes, here. This is the dilution zone actually. Okay. So this is your dilution zone. Okay. So the remaining air referred to as a secondary or dilution air, okay, is admitted into the liner, okay, into the liners, okay, in a controlled manner, okay, in a controlled manner. So that one also you just remember, okay. So now we go here. The secondary air controls the flame pattern, cools the liner wall. That is what I mentioned there. Okay. The secondary air controls the flame pattern, cools the liner wall, dilute the temperature of the core gases and provides a mass. Okay. So this cooling air is very critical as the flame temperature is above 1930 degrees C, which is higher than the metal endure. Okay, metal can endure. Okay, so it is important that the fuel nozzle, combustion liner control the burning and mixing of fuel and air under all conditions. What for? To avoid excess temperature reaching the turbine or combustion cases. Okay, that is the point. So the rare third of the combustion liner is the transition section. So basically the transition section has a very convergent duct shape. So here we are talking about divergent, right? So the third of the combustion liner as a is as a transition section wherein it has a very convergent duct shape, okay, which begins accelerating the gas stream and reducing the static pressure in preparation for entrance to the turbine section. So that is the point. Just remember, okay, good to go. So we are done with this, okay, combustion. Okay, now we go into the turbine and exhaust section. So a section. So the turbine converts the gaseous energy of the air burn fuel mixture out of the combustor to mechanical energy needed to drive the compressor, driven accessories, and through a reduction gear and the propeller. Okay, so the turbine converts gaseous energy into mechanical energy. How? By expanding hot, high pressure gas to lower temperature and pressure. You got it, friends? Just remember this, very important. So each stage of turbine consists of a row of stationary vane followed by a row of rotary blades. This is also a point to note. So this is basically a reverse order of the compressor. What is that reverse order? You see here, in the compressor, energy is added to the gas, right, by the rotor blade, right, then converted to static pressure by the stationary stator bands, right? Okay. In turbine, the stator wind increase the gas velocity and then the rotor blade extract energy. This is a bit of a confusion, but you have to remember this. So I repeat again, each stage of the turbine consists of a row of stationary winds followed by the rotary wind. But in the other case, it is like that. First rotary blade, then stationary. So this is what I meant here. This is the reverse of the order of compressor. So in a compressor, energy is added to the gas by the rotor blade, then converted into static pressure by the stationary stator wind. In the turbine, the stator wind increases the gas velocity, then the rotor blades extract the energy. Okay, so that is the point, friends. Yeah. Then the vans and the blades of the airfoil type. Airfoil means, you remember the flight, you have these wings, right? Yeah, that kind of shape, okay? That provide for a smooth flow of gas. As airstream enter the turbine section from combustion section, it is accelerated through the first stage of the starter van, first stage. Then the starter van form convergent act, as I mentioned in the previous slide, that convert the gaseous heat and pressure energy into a higher velocity flow. Okay. So in addition to accelerating the gas, the vans turn the flow to direct it into the rotor. Okay. Rotor blades at the optimum angle. So as a mass of the high velocity gas flows across the turbine blade, the gaseous energy is converted to mechanical energy. So that is the point. Okay. So velocity, temperature, pressure of gas are sacrificed in order to rotate the turbine to generate the shaft power. That's it, friends. Very simple, isn't it? Okay. So a few more. The use of properly positioned airfoil allows a smooth flow and expansion of gas through blades and vents, right? So all the air must flow through airfoils to achieve maximum efficiency in the turbine. So in order to ensure this, seals are used at the base of the van to minimize gas flow around the van instead of through the intended gas path. So in addition, first three stages of turbine blades have a tip shrouds. What for? To minimize the gas flow around the blade tips. So in an ideal gas turbine, gases undergo thermodynamic process, which you know, is a Brayton cycle, right? So isentric compression, isobaric combustion, that is a constant pressure, and we have an isentric expansion. Compression, combustion and expansion. Okay, that's it, friends. So we are done with this. And in practical class, see, this is ideal case, right? Ideal case. But practically, mechanical energy is irreversibly transformed in heat when gas is compressed due to internal friction and turbulence. So the passage to the combustion chamber where heat is added and specific volume of gas increases is accompanied by the slight loss in the pressure, just for your info. So during the expansion phase, stator or rotor blades of the turbine, irreversible energy transformation once again occurs. Okay. So just remember this, no need to worry much on this section. Okay. Now we go into the open cycle and closed cycle. We also talked about that in the model actually when we discussed. See, most gas turbines operate in an open cycle mode where air is taken in, right? Air is taken in from the atmosphere and discharged back to the atmosphere. Okay, discharged back. Okay, so yeah, the hot air being cooled naturally after exit the turbine, natural cooling. But in a closed cycle, the working fluid air is continuously recycled by cooling exhaust air through heat exchanger. This guy, we are using this and directing back to the inlet. So in a closed system, combustion cannot be sustained and normal combustor is replaced with a secondary heat exchanger to heat the compressed air before it enters the turbine. Okay, so this heat is supplied by an external source such as maybe a nuclear reactor or maybe fluidized bed of coal combustion process. This is about the simple talk on this open and closed cycle, friends. So that's all I have on this topic. So hope I have given as much as information to you. Of course, I know you might have had challenges in visualizing, but yeah, this is how we need to learn, because unfortunately I don't have any animation. If animation is there, it could have been better. But nevertheless, something is better than nothing. Yeah. Thanks for watching. So see you in the next video wherein we'll focus on the axial flow compressor that is asked by one of our friends, and yeah, many more to come, friends. Stay tuned and yeah, keep us supporting. Thanks for watching. Bye bye, take care.